Hello dear students, welcome to Pen and Paper Chemistry. With this video we are continuing with our topic states of matter. In the previous video we have already discussed the properties of the different forms or states of matter. We have also discussed about thermal energy and intermolecular forces, the different units of physical quantities that we shall be talking about in this unit, and also the relationship between them. Yes, you can use these triangular conversion charts, and if you want you can also add units to according to your curriculum. So for example, we decimeter cube, yes, it's the same as liters, so you can add these to your learning charts and observe them daily. Just observe them daily, and within 2 days all your concepts, all your conversions will be clear. Same way for temperature as well as volume. What are we going to do today? We are starting with the gas laws. Very important laws which you can understand from daily observation as well. Although it took a long time for the scientists to crack the relationship between the pressure, volume, temperature and mass of a gas. These are the physical values in the form of which a gas is characterized, right? So if you see a cylinder in which gas is trapped, you will find that on the cylinder you will find the marking as to how much is the mass of the gas. So let us suppose we say it says 14 kg, at what pressure it is and at what temperature is safe for the cylinder to be stored. So these are characteristics in which a gas is defined. What are we doing in the gas laws? We will try and derive a relation between these various physical quantities. So pressure, volume, temperature and mass. But do you think it is easy to derive a relation between all four of them in one go? It's difficult, right? So what are we going to do is, we are going to take two physical quantities at one time and are going to take the other two as constant. So we are going to derive a relation between pressure and volume, volume and temperature, volume and mass. Yes, these relationships were given by different scientists at different times, and accordingly these have been named as Boyle's law, Charles' law and Avogadro's law. So when I want to talk about pressure and volume, what are the two physical quantities that I'm going to take constant? Yes, temperature and mass. We are not going to disturb them. That means during the entire set of observations or experiments that were done in order to determine the relationship between pressure and volume, the temperature and the mass were kept constant. We took a fixed mass of the gas and kept the temperature constant. And it is called as the Boyle's law. Second, we derived a relation between volume and temperature. And of course, the other two quantities which are left are pressure and mass, which are observed constant. And this will give us what we call as Charles' law. Same way, volume and mass. Obviously, we are going to take the temperature and pressure as constant, and we would call it as the Avogadro's law. So, are you ready with your pen and paper? Yes, I'm sure you would have made a separate notebook by now so that you have your notes ready for offline reference. Yes, I love that confidence and the smile. Boyle's law was given by Robert Boyle in 1662 after a lot of experimentation and lot of observations. Now we are not going to talk about that. What we are going to do is I'm going to talk about simple general observation that you can easily make. So volume. Volume means the space occupied by any substance, be it solid, liquid or gas. You have a certain volume. You are sitting, you are occupying a certain region in space. That's your volume. Pressure, the force acting per unit area. So what happens is, if I have a stick and I am applying pressure onto a block with the help of this stick, right? The force acting per unit area is what we will call as pressure. We increase the area, pressure will decrease, because pressure and area are inversely proportional to one another. In the first video, we have also discussed about the units. Now, you notice over here that this gas is occupying a certain volume under a pressure from the piston, which we are applying pressure onto this gas with the help of this piston. Now what will happen? Supposing you try to push the piston down. Obviously the gas will try to push it back, right? Now you try to push the piston down and you manage to force it down. So what we say is, now the piston reaches here. Okay? You are not allowing the gas to escape. In other words, the mass of the gas has to be constant. There should be no leakage of gas from this setup. Secondly, during this entire setup, we will take the temperature. We will also maintain the temperature as constant. So what we are going to do is, we are going to compress the gas very slowly. When we compress the gas, compressing means we are reducing its volume, right? So let us suppose that the volume of the gas now becomes V by 2. That means it becomes halved. Tell me, did you have to increase the pressure or decrease the pressure? Yes, you applied the pressure. You increased the pressure in order to decrease the volume, right? So if pressure is increasing, the volume is decreasing, right? Now let's talk about the reverse. So what we have over here is, now let's suppose you pull the piston out. So what you are going to do is, you have this piston and again let's say the volume of the gas is V. Now slowly and slowly you pull the piston out. Now when you pull the piston out, so it comes up, right? Pulling the piston out means, is the pressure on the gas increasing or decreasing? So how will the piston be pushed out? Yes, the gas will push it out. So in other words, your pressure is reducing, correct? So the volume here has increased when the pressure over here has decreased, right? So when pressure decreases, volume, yes, absolutely, it increases. So what kind of a variation is this? You've done in mathematics. When one increases, the other decreases. What do you call this as? Is it a direct variation or inverse? Absolutely, it's an inverse variation. In other words, how do we denote it mathematically? We will say pressure is inversely proportional to volume when the mass and temperature of the gas are kept constant, right? So let us define our Boyle's law. Now here you have to remember that there are certain terms which are very, very important. First of all, at constant temperature, please make sure that you underline it, because while deriving relation between pressure and volume, we are keeping the temperature as constant, right? At constant temperature, volume of a fixed mass. Again, in this definition, please do not forget the term fixed mass of gas is inversely proportional to the pressure applied, right? So let us again list the mathematical expression for Boyle's law, and please don't forget to write mass and temperature are constant, right? Good. Please make a note of this. Now let us derive a formula out of this. So removing the proportionality sign, we put a constant K. Take P to the left hand side, so we have product of PV is a constant, right? So if at the same temperature for a fixed mass of gas, I have two sets of values for pressure and volume. So in other words, if at pressure P1, the volume of the gas is V1. At pressure P2, volume of the gas is V2. Then the two products are constant and fixed, and so P1 V1 is equals to P2 V2, and that gives us the first formula of this particular chapter. Now remember over here, when you are doing questions based on this, you make sure that the units of the pressure and the volume on both sides are same. No matter what units you take, it doesn't make a difference. If you are taking atmosphere on the left hand side, make sure that the pressure on the right hand side is also expressed as atmosphere. If you are expressing it as bar, make sure that the pressure on the right hand side is also a bar. And there should be no difficulty at all. Have you noted this down? Because now we are going on to the next aspect, and that is what we call as the graphical representation of Boyle's law. We've just now seen that pressure is inversely proportional to volume, right? So you notice the shape of the graph. When the pressure increases, the volume is decreasing, and this is how we have the graph. What about pressure and inverse of volume? Pressure is inversely proportional to volume, agreed. But what if I take the inverse of volume? Yes. So as a whole, if I am talking about this 1 upon V as one physical quantity, then pressure will be directly proportional to 1 upon V. In other words, what kind of graph do I get? Yes, it will be a straight line graph. Okay, what about PV? Just now we said that product of pressure and volume is constant irrespective of whatever is the value of P or V. In other words, I will get a graph which is parallel to the x-axis. On the x-axis, you can either take pressure or take volume. The value P into V for a fixed mass at constant temperature will remain the same. Now, what we need to understand over here is the variation of these graphs, or the change in these graphs when you change the temperature. What do you think will happen? Will PV remain the same? The product of P into V will still remain constant. PV will still remain constant, but that value will be different from the graph that you have drawn or the value that you would have calculated earlier. What we will find over here is, again, with increase in temperature, we will find that the graph changes. So I have the first graph at temperature T1, the second graph at temperature T2, where T2 is greater than T1, right? What happens to the graph of pressure against the inverse of volume? Again, what will happen? Yes, the slope will increase. So what will happen is, now your second graph will be like this. Make sure that you draw these graphs with pencil, ruler, nice clear graphs, right? Again, with increase in temperature, the slope increases. Again, come to this one. PV is constant, but this is the value at temperature T1. Now, if I change the temperature, let's say I take the temperature T2, where again T2 is greater than T1, then this PV will change, and here we will have a graph which is lying higher than the value which is there at T1. So this is our PV graph at temperature T2. I hope you are drawing these graphs, because these will come in very, very handy in giving you a full understanding of the concept. Observe these graphs carefully, draw them carefully, pause the video, explain, understand. If you don't, just don't copy them just because they are on the screen. Understand, go logically, try. Now, what are these graphs called as? So the first graphs that we drew, a graph wherein what is happening is you're drawing these graphs at constant temperature. That means the temperature does not change. What are such lines called as? Temperature is remaining the same. So isotherm. Remember, from thermodynamics, we have already dealt with the topic of thermodynamics in a separate playlist, and each graph, so this graph that we've got is an isotherm for the gas at temperature T1, the white curve. On the other hand, T2, this is the isotherm at temperature T2, right? Now, would you like to understand the practical application of this particular law? So, we are going to see how this concept is useful in the daily life. I am taking up a question over here. The first question, you see it is listed over here. If you've understood the topic, why don't you try this question yourself? It says, a sample of CNG has a volume of 880 decimeter cube at a pressure of 0.2 bar. Now, by the way, these values are all hypothetical. I've just framed this question in order to give you a practice. That doesn't mean that practically you'll get these values only. What pressure is required to fill it in a cylinder of capacity 44 decimeter cube? Come on, give it a try. Try this question yourself. I will guide you in attempting this question by telling you how to attempt any numerical, not just this one. So your first thing is, you list down the values which are provided to you. A sample of CNG has a volume of 880 decimeter cube. So that's my first volume, right? So 880 decimeter cube. Make sure that you write the unit as well. At a pressure of 0.2 bar, that means the pressure at which the gas is occupying 880 decimeter cube is 0.2 bar. Now, what do I have to find out? What pressure is required to fill it in a cylinder of capacity 44 decimeter cube? So, what do I have to find out? Yes, I have to find out the pressure at which the volume of the gas is 44 dm cube. Yes, simple. So, what do? P1 V1 is equals to P2 V2, right? Go ahead, put the values. Now, before you put the values, a very, very important point. Check the units. Are they same? Yes, decimeter cube, decimeter cube. This is bar, so obviously the pressure that I will get over here would be in bar. So 880 into 0.2 divided by 44 gives me the value of P2. Please calculate this for me. Got the answer? Okay, let's do one more question. A hydrogen balloon can withstand a maximum pressure of 0.2 bar. Hydrogen occupies 22.4 liters at 1 bar pressure. What is the maximum volume of hydrogen which can be filled in the balloon before it bursts? Right, so you want to play safe. We don't want our balloon to burst. So let's try this question. Oh, good, if you've already calculated it. Very good, then you go ahead and attempt some questions from the books that you've got. It says hydrogen balloon can withstand a maximum pressure of 0.2 bar. So do I need this value as of now? No. Hydrogen occupies 22.4 liters at 1 bar pressure. Okay, this is an important piece of information. So the hydrogen gas is occupying 22.4 liters at a pressure of 1 bar. Again, it's a hypothetical question, nothing got to do with real life. What is the maximum volume of hydrogen which can be filled in the balloon before it bursts? Now, before it bursts means I have to maintain the pressure maximum. This much. I cannot exceed this much pressure more than 0.2 bar because the balloon is going to burst. So I need to find out the volume of the gas which can be filled into this balloon without it bursting. See, our first step is done. While reading the question itself, I jotted down the data. So you have the data. The next thing that you need to do is to check the units. Are the units same? Bar, bar, correct. This is in liters, so obviously my answer for volume would be in liters. Now why don't you try this question? Give me the answer. Go ahead. I'm waiting for you to do this question. Just don't look at the screen. Nothing is happening. Go ahead, do it. Okay, I have calculated over here. Tell me whether my answer is right or wrong. You be the teacher for me. Okay? Now let us derive an interesting observation from here. We know that PV is constant. Okay, by the way, pressure is usually represented by a small p, but can be seen as being represented by a capital V in many places, as you would have observed I have done during the video. But the norm is to use a small p. Okay, sorry if I have misled you. Now coming back to Boyle's law, pressure into volume is constant, right? Now, what is volume equal to? We say density is the mass per unit volume of a substance, right? So, I can write volume as equal to mass divided by density. So, that will again remain as a constant. right? Now what did we say when we defined Boyle's law? That mass is also constant during the course of this reaction, or sorry, during the course of this process. In other words, pressure upon density is also constant, right? So what we can say, pressure is directly proportional to density. Now why am I leading you into all this? What does density mean? What do you understand by density? Of course, one is the definition, the mathematical bit of it, where we say density is the mass per unit volume of a substance. Density also defines how close the particles of a medium are. Higher density means closer are the particles, right? So density is a measure of the closeness of the particles of a system. Now, when I am saying that I have a cylinder and I increase the pressure on it, right? So what happens? Volume decreases, right? Mass is constant. The particles which were otherwise, let's suppose the original situation was something like this, the particles were spread out in a bigger volume, now become huddled up closer, right? The particles come closer to each other. Now, when the particles come closer to each other, that means the density has increased, right? So, when pressure increases, density also increases. Now, near the sea, right? What is happening here? The air is under pressure from the layers above it. So what will happen is, at sea level, the density of the air is more because the pressure is more, right? Now, when you go to higher heights, on the other hand, if you go to higher altitudes, right, to the mountain tops, what will happen? There, the volume increases, the pressure of the surrounding air is much less, right? The particles are further away. That means at higher altitude. I hope you are noting this down. Yes, at higher altitude, pressure decreases, density also decreases. Density means closeness of particles decreases. Now, when the particles are less close to each other, that means if you are breathing, then are you getting enough oxygen? Oh, what a drawing I have made over here, right? Are you getting enough oxygen through the air that you are inhaling? No, because the density is less, there is less oxygen. Of course, the air is more pure, but there is less oxygen in a given volume of air. That is why we tend to feel breathless at higher altitudes, and we need to train our breathing in order to adapt our body to living in higher altitude conditions. Now here, I'm sure you must have observed sometime or the other that people living in higher altitudes usually have, a reddish glow on their skin. Yes, it's bright red. And why do you think it is like that? Of course, they are eating much healthy food. So, but what about their skin? Their skin is slightly more reddish. Can you think of a reason why it is like that? Think, and think as to why we would be talking about it at this point of our lesson. So now that you've learned the first law, what is the homework for you? Numericals. Real sore point for some students. But before you go on to do numericals, I would request you to clear your concept of linear equations if you are not thorough with that, because without that you will find yourself struggling in the numericals bit of it. Before you watch the next video on the channel, please make sure that you have practiced at least 10 questions based on this particular law, and you come back smiling for the next law, wherein we are going to talk about, yes, we'll be talking about Charles' law and making chemistry easy and fun to learn. Stay safe, stay happy, and stay healthy. See you in the next video.